Thanks, Steve. Hi, everyone. Thanks for joining me today. Today we are going to discuss about US presidential election. I know it's a very tempting topic, especially with the third debate coming up. Don't worry, we are not going to discuss about US presidential election. But what we are going to discuss is the protocol which we love all, which is BGP. So my name is Rohit. I work for Brocade. So let's begin. So we have a very packed agenda. What I'm going to do is first give you an idea why we need to enhance BGP, what are the new use cases of BGP, and what exactly we are trying to achieve with the new services being deployed with BGP as the core. So the design goal of BGP when it started was to connect networks to provide inter-domain routing so that something called internet can exist. But over a period of time, what we see, internet started to grow, bandwidth started to grow, even the internet-based services like cloud services, multimedia services, or the other services are going like crazy. So with the ever-growing demand of new services, we need to enhance BGP so that it can support the requirement of new services. Why BGP? So the first thing which comes to my mind is investment protection. So once your operation team knows how to deal with BGP, how to deploy BGP, how to troubleshoot BGP, it's very easy from a service provider perspective to deploy new services. So let's say if you have enabled BGP for internet peering, and then you have a requirement of providing VPN services. So what you have to do, you have to just enable the new services by adding the new NLRI, and your BGP is up. So from the operation perspective, the team doesn't need to learn any new routing protocol. They are fine with BGP because they have operational experience with BGP. Other thing is it's very low overhead. So once you send an update with BGP, it's not chatty. It just provides the incremental updates after that. Scalability is one of the key features of BGP. It's proven with time. High availability, we'll see these features, how BGP provides high availability. Multi-protocol. So again, as I said, basically we have different address families which can be enabled with BGP, whether it's IPv4, whether it's IPv6, whether it's L2 VPN or L3 VPN services. And moreover, it is very flexible when it comes in terms of policy enforcement. So this is a very important slide where you see all of the services are kind of moving towards BGP. So you will see a pattern in my presentation. There are three important patterns. You will see some of the services use BGP as the signaling protocol. Some of the services will actually enable the NLRI so that they can go to the next services. And some of the services you will see there's a new kind of attributes being added in BGP to support those kind of functionality. So in the past, BGP was primarily used for internet peering and L3 VPN services. But over a period of time, you will see it is being used for multicast services, L2 services like EVPN, DDoS protection, which is used by BGP flow spec, network monitoring. So you see it is traditionally being used by SNMP, but now we are moving towards BGP monitoring protocol. When you talk about data center, you still use BGP in forms of BGP LS or BGP EVPNs. You talk about multiple MPLS transport, you use BGP as the transport. And when it comes to SDN enabled services, we still use BGP in different forms. So what I'm going to do is give you an update about these new services, why we need to enhance BGP, and how BGP is actually playing a key role in enabling this new generation of services. So let's talk about BGP infra advancements. So from infra perspective, it is not related to protocol as such, but when it comes to the BGP stack deployment, it is very important Because with the next generation of services, they demand more scale, more reliability, less convergence, and more robustness. So what are the choices for a BGP stack implementation perspective? You have a choice from going from 32-bit OS to 60-bit OS. You can have BGP deployed in multi-processes. You can use multi-core strategy, or you can also go with TCP transport implementations and improvements on that. So I've listed few of the important BGP processes and how they are going to play an important role for BGP. So in the past, BGP uses three important process: update process, keep alive process, and route refresh. They were all bundled in the same process. So usually the problem with having a single process oriented BGP implementation, you will lose many packets in time of congestion. So give an example, assume if you are losing keep alives, the problem can be your session might be flapping. Update generation enhancements. This is again one of the important BGP process where it depends on how you actually generate the updates. So instead of having a bundle of process, you can implement update generation as a separate process. So the advantage you gain is you get more CPU cycles. Parallel route refresh. So imagine a situation where route reflector has to do route refresh as well as incremental updates. So many times we observe that this becomes a bottleneck for RR. It takes a lot of time for incremental updates. And especially if you have a slow peer in your network, right? So imagine you have a BGP speaker which needs to have thousands of peering sessions and millions of BGP prefixes. So in that kind of environment, it becomes very difficult when you have slow peers in your network. So what can be done is your implementation can identify slow peers. They can put into a separate update group so that the other peers are not impacted due to slow peer in your network. Another important advancement in infrastructure is adaptive cache. So instead of deploying BGP and giving it a fixed memory size, what can be done depending on your address family use, you can actually have a circular buffer, which basically is dynamic way of allocating memory. Next, we'll talk about high availability. So the first thing which comes to my mind when we talk about high availability is convergence and resiliency. So I'll just give few examples of the new advancements in BGP in terms of high availability. Let us talk about BGP graceful shutdown. So don't confuse it with BGP graceful restart. So the primary difference between graceful shutdown and graceful restart is, let's imagine a situation where we want to do maintenance of a BGP router. So, or we want to decommission a BGP router. So in this kind of scenarios, what you want that your peering neighbor should somehow know that, yes, I'm going for maintenance. So you have two options. Either your software should be robust enough to handle maintenance and without any loss of traffic, or you should somehow tell your neighbor that, yes, I'm going for maintenance, so you redirect your traffic to some other path. The first choice is very costly operation because it has to be implemented in such a way that it would require a lot of CPU cycles and a lot of memory. So that's costly affair. The other option, which is implemented using graceful shutdown. So if you see the diagram, what happens when the router is going for maintenance? What it does, it sends all its advertised prefixes to its neighbor, and it also attach a well-known community called gshut. What it can also do is it can also send a local preference value which is lower. So it is kind of a trigger to the peering neighbor that, yes, I'm going for maintenance, so you need to redirect your traffic to some other guy. Now the guy who's receiving the gshut community can actually have an inbound policy where it lowers the LP for the guy who is going for maintenance and then can redirect the traffic to some other guy. So in that way, it can be done. Prefix independent convergence. So in the past, when BGP used to converge, it used to take more than 4 minutes and 5 minutes, and it was still acceptable because that point of time we used to talk bandwidth in terms of kbps or baud. But now imagine a situation for today's kind of services where we talk about bandwidth in terms of gbps and tens of gbps. So 1 second of convergence time itself is a huge cost to the transit provider, and especially when the service providers give services to its customers, they have very strict SLAs to meet. So with that kind of requirement, it is highly impossible to have a convergence time in minutes or in seconds. So what prefix independent convergence does is it is kind of a BGP fast readout technique. In any fast readout technique, whether it's MPLS based fast readout technique or it's IPFRR fast readout techniques. So essentially what we do, we compute a primary and secondary path before the failure happens. And in the event of failures, what we do, we already have the secondary path installed in our data plane. We just move the traffic to the secondary path and then re-optimize. So in that way, you achieve very, very high convergence. So PIC actually comes in 2 flavors, PIC core and PIC edge. So what it does, it basically protects your core link failures or your edge link failures. Especially in comes, it is helpful when your customers are dual home to your network. So this is one example where we know how PIC can converge your network in sub-seconds. So let's take an example where P3 is the primary path and P4 is the backup path. So your traffic is coming from C1 to C2. Assume that the link between P3 and C2 has gone down. So what happens? Your data plane will detect the link failure event. So if you have BFD enabled, it is much faster. Once it knows that your primary link goes down, it will automatically shunt the traffic to the secondary path, which is via P4. So what you are achieving with this, you are not actually waiting for your control plane to converge and then take the path to P4. You already have a secondary path installed in your data plane, and then you are moving the traffic as quickly as possible. Now, think from the control plane's perspective, right? So once the failure has been detected, BGP will withdraw its primary path. It will recompute the best path selection with the available paths, and then it will move the traffic to the next available path. So now let us talk about multipath. So the way BGP operates is it calculates the single best path and then it basically advertises that best path to its neighbors. Now the problem with single best path is we can't do much of traffic engineering based out of BGP. So if you have a way, a mechanism where your BGP can actually have multiple paths in its forwarding, then you can achieve many advantages. One is your convergence becomes much faster. So what we see in the BGP prefix independent convergence, we need to have at least 2 paths, right? One is your primary path, which is used for your primary sending the traffic over the primary path. Another, in case of events of failures, you need a backup path so that your data plane doesn't need to wait for your control plane convergence. Another advantage with multipath is you can do ECMP load balancing, and this is primarily required in DC environment. Prevents oscillations. So oscillation is a problem where in your network you advertise and withdraw routes multiple times. This is mostly induced with MED or with RR kind of implementations. So if you have multipath enabled, you can actually bypass those kind of problems, if not completely avoid that. And another advantage with multipath is it allows hot potato routing. So imagine you are a transit service providers. For you, it is very important to send the traffic as quickly as possible from your network, because it basically boils down to, for you it is kind of, very important to send the traffic as soon as possible, because the more the traffic will remain in your network, it will be more costly for you. So just a quick recap of the BGP best path selection algorithm. So the important thing to notice here is the point where we are doing multipath. So you just see the attributes before IEBGP multipaths are known as topological independent attributes. So I'm talking about local preference, shortest AS, lowest origin, or MED. So there doesn't actually depend on your topological placement of your BGP speaker. So the other parameters like lowest IGP metric, your lowest router ID, and eBGP over IBGP are topological dependent attributes. So once you enable the multipath knob in your router and all the parameters before IEBGP multipaths are same, you do multipath on your router. Or if you want to do eBGP based multipath, then you will still consider the next hop metric to IGP metric to next hop. So let us see the impact of best path selection. So in this case, the prefix Z is actually reachable via P2 and P3. So P2 and P3 learn this external prefix and then advertise to RR. So what RR does, it basically recomputes the best path and then send a single best path to P1. So from P1 perspective, still its network P2 and P3 have multiple paths. The other path is not visible because of BGP, the way BGP works, it only advertises a single best path. So this is the impact of the best path algorithm. The other impact is when you have different internal policy configured in your network. So same scenario, I have a prefix Z, I have learned the prefix from P2 and P3. And now what I'm doing, I have a pairing between P2 and P3, IBGP pairing. And what I'm doing, I am increasing the LP for the path which is reachable via P2. Now, from P3 perspective, it also gets the path from P2 with higher local preference. Now, P3, what it does, it actually withdraws the path which it advertises to P1. Again, the problem, P1 have a single best path. So what are the solutions so that we can actually use multipath effectively? So we'll go one by one. What are the solutions? If you are an MPLS VPN provider, for you, the best way to achieve multipath is unique RD per VRF. So now the same scenario, what we are achieving? We are learning the path Z over P2 and P3. Now, since my RD is unique over VRF, I will give those paths to my RR. Now, RR will consider those paths as unique because your RDs are unique. From P1 perspective, both the paths via P2 and P3 now visible. BGP best external. So this is one of the key feature of BGP which is used widely. Again, same scenario. I have two paths via P2 and P3. So in the previous case, right, when we have the LP increased, which is the policy impact, now what P2 will do, still it will advertise its own best external to P1. So primarily what we are doing is, Even I have a best path learned via IBGP over PE3, I will still advertise my own best external to PE1. So now PE1 will have path visibility via both PE2 and PE3. BGP add path. So don't confuse multipath with add path. Add path is a capability which has to be negotiated between the BGP speakers. So what essentially it does is, again, the problem of advertising only a single best path in BGP. So via add path, what we are achieving is, instead of only reflecting a single best path, I can have this capability negotiated between my receivers and senders. And primarily what I do, I can advertise more than one path into my BGP. So it is an extension of BGP diverse path, which used to send only two best paths. Add path comes in different flavors. So you can have n best paths. So primarily what BGP does, it calculates one best path and n-1 backup paths. Or you can have all best paths, where it will select all best path and send to its peer. Or you can have multipath. So in that case, you have one best path and then n-1 ECMP paths. So the primary goal, what we are achieving with add path, is path visibility, and which brings path diversity into your network, because you have now multiple paths visible when you use add path. So now let us talk about hot potato with full mesh. So imagine a situation where we have two geographies, Europe and US, and I have two routers in London and Paris, and in US side, Boston and New York. So when I have full mesh pairing between all the routers, the path to Z is visible via New York and Paris from US side, and via New York and Paris from European side as well. So what you achieve with full mesh is, you have both the path visible, and you basically choose the shortest path available from your own geography. Now you put a RR in between. So what has been done, we have put a route reflector in US geography. Now it breaks the hot potato. How? Since the RR is placed in the US geography, from RR perspective, it will select New York as the best path. And it will also reflect that path to the other peers, which is, let's say, London. So now the traffic from London has to go all the way from Boston to New York to reach the prefix. So the problem is, once you put RR, it will calculate the best path from its own perspective. And essentially what matters is the distance of next hop reachability from RR perspective. So to avoid that, what could have been done is, we could have placed another RR in Europe region, and then we could have sorted out this problem. But imagine a large tier 1 ISP which have a very, very huge network, and just imagine the number of RRs it can have, maybe thousands. The full mesh of those many RRs is a costly affair, and it's not advisable to do all the time. So what is an alternative solution is something known as optimal route reflection. So it comes in 3 different flavors. So first, we can enable add path everywhere. So as I mentioned, add path is essentially a capability in BGP which has to be negotiated between sender and receiver. But the problem with add path is, it requires more and more memory. So it might happen that in your network there are some slow peers or some old routers which may not support add path functionality. Another option what we can use is RR based optimal route reflection. So in this case, what we essentially are doing is, we are calculating the IGP next hop from RR, thinking that RR itself is a client. So what I'm saying, imagine the same situations. So the RR, instead of calculating the path via Boston, via New York, what it does, it assumes itself to be located in the European region, and then it basically calculates the SPF thinking London as the route. So what essentially it will do, it will calculate the best path not from its own perspective, but from its client perspective. But the problem with this kind of approach is RR has to run many SPF calculations. So if you have different clients, on number of clients are growing, the number of SPF calculation will also grow on RR. And other than that, it also has to maintain different RIP for each client. And the way it advertises the updates in BGP also has to change depending on the client locations. Third option is RR client BGP assisted ORR. So where actually you distribute the SPF calculations on clients rather than on RR. Now let's move to BGP VPN enhancements. This is one of my favorite topic, L3 VPN IBGP as PC protocol. So in the past, we have different protocols being supported as PEC protocol for L3 VPN, whether it's OSPF, ISIS, or eBGP. But we couldn't support IBGP as the PEC protocol. The obvious reason is BGP split horizon, because the IBGP learned routes will not be advertised to other IBGP in the service provider backbone. So with this enhancement, what we are achieving is we can use IBGP as your PEC protocol. And the advantage what we gain is now you can actually transport all your customer attributes in BGP over the service provider and then send to the other side. To achieve this kind of enhancement, the PE router has to do two functions. So essentially what it has to do, first it has to support VRF kind of functionality within RR kind of functionality within the VRF, and it has to treat the client as the internal client. It has to consider the customer side as the internal client. Other thing what service provider has to do, it has to carry the entire BGP attributes of clients into a new attribute called attribute set, and then transparently transport those attributes over the service provider backbone. eVPN. So yet another Ethernet L2 VPN services. So why we need eVPN when we already have something called VPWS or VPLS? In the past, we have two products to provide L2 VPN kind of services, VPWS and VPLS. So VPLS is basically a multi-point service where you advertise the pseudo wires over BGP. The problem with VPWS is it doesn't cater to the new requirement, which is essentially driven by DC, data center interconnect. So what essentially the DCI or data center interconnect requirements are, it has to transport a large volume of MAC addresses from one side to the other side. And it also requires per flow load balancing and ECMP paths over different sites. So VPLS is not meant for that. What essentially we are achieving with VPN, eVPN is you actually transport your MAC addresses into a separate BGP NRI that is known as BGP eVPN NRI. And you can also transport MAC as well as IP over eVPN. So it has two types, type 1 and type 4. Type 1 is essentially carrying your MAC addresses across your backbone. Or you can also carry MAC as well as IP. So IP is essentially required to provide proxy ARP kind of functionality. With eVPN, essentially the target to achieve is integrated services over the same interface. So currently we have L3 VPN separately as NRI and L2 VPN a separate NRI. With eVPN, we can actually achieve both L2 and L3 integrated VPN functionality using eVPN. So let's assume that you have a branch and headquarters. So between the headquarters, you may want to do only L2 VPN services, and between your headquarters and branch, you want to do only L3 VPN services. So those kind of services are possible using eVPN. Other than that, what it achieves, since now I am addressing MAC address as part of my NLRI, so it's kind of MAC routing. So what I essentially can do, if I am multi-home to different providers in provider environment, I can advertise certain set of MAC in one P and then certain set of MAC in another P. In that way, I can actually achieve ECMP. Other thing is possible with eVPN is per flow load balancing, which is not possible in case of VPWS. Yes, in case of VPWS, what can be achieved is per VLAN load balancing. But let's assume when there are a lot of traffic being hit on that particular VLAN, then you essentially have to redesign your network manually. So there is no automatic fallback from one VLAN to another VLAN. Also, with eVPN, we have different types of routes. We have something called MAC mass withdraw, so which is essentially useful when there's link being down in one site, so that all MAC addresses has to be removed. So other important difference between eVPN and VPWS or VPLS is VPLS works basically as a bridge. So the learning how VPLS does is it has to do data plane forwarding, and then from data plane forwarding basically it learns the MAC addresses. Whereas in eVPN we actually advertise the MAC as part of eVPN LRI. BGP for SDN. So software defined network. So as we know, it's a new paradigm in networking world. There are many definitions of SDN, how it works. Essentially, it solves two problems. It basically segregates your control plane from your data plane, and it provides network programmability through open interfaces. So why BGP is needed in SDN? So there are many use cases. I just wanted to cover few of them. Essentially, BGP link state. So traditionally, if you see the traffic engineering through RSVP, it has a well-known problem as bin packing or suboptimal path computation when it comes to inter-AS or domain inter-AS or inter-area path computation. So what you can achieve with BGP, again, BGP LS is another NLRI. So you can actually advertise your link states which are learned over either ISIS or OSPF, and then advertise those link state information into BGP. So from the domain perspective, BGP can run iBGP with BGP LS extensions with this RR. So RR will know essentially all the interlink state information. And then RR needs to have a single BGP session with path computation element or controller, so that the controller will know all the link state information. So essentially what the path computation element can do is it calculates the path and then creates something called traffic engineering database. So now this traffic engineering database can be consumed by the applications, and it can compute the path and signal the head node. BGP persistence. In certain scenarios, there is a requirement of some of the NLRIs to not be withdrawn even the BGP session is down. So one of the key area or one of the key important feature is BGP flow spec. I think next session is BGP flow spec, so you will know why it is important. So just to give a brief overview of flow spec, it actually carries your policies, your DDoS protection policies using BGP updates. So in certain scenarios, and the way it is implemented is using controller. So there might be a case that your controller needs maintenance or it goes for reboot. So in those kind of scenarios, you still don't want that all your BGP policies through flow specs are moved from your devices. You still want to keep those prefixes or those policies inside your router. So what essentially you do is, again, it is based off per NRI. So let's say if you have internet-based NRI or IPv4 NRI, you still want the prefixes to be withdrawn, but you don't want the DDoS protection or security policies to go out from your device or from your networks. BMP. So when we receive updates, what a BGP speaker does, it basically have inbound policy. It runs the inbound policy over the updates received, and then essentially it put that routes after the inbound policy it's into its RIP, and then finally it moves out those policies to its peers. So what we are trying to achieve with BMP is a monitoring protocol. So instead of sending the RIP entries to a controller, what is essentially done in NetFlow, what it does is it basically, before even applying any policies to raw BGP updates, the BGP client will actually send the BMP client will actually send those updates to a centralized controller. So it essentially forms a database of all the BGP updates, which is learned over your peers. So essentially what you achieve with BMP is different kind of functionalities at the application layer. So you can actually do looking glass. You can have route analytics, which basically tracks your convergence times or history of different prefixes when they change over a period of time. You can also do traffic engineering analytics. So basically, again, it is important from analytics perspective. What are the different types of path visible from your network? And lastly, you can also do BGP per policy what ifs. So what essentially it does is, before you actually apply any policy, you have the entire database available to you. You abstract those information, and then you try to apply different kind of policy and see how does it impact your network. So essentially, instead of applying the policy and then doing the policy-based function on production, you can actually use BMP to do that. So these are others cool feature which may interest you. This may be the next session which I can plan is, so far what I discussed is some of the examples of BGP features which are used in, especially in service provider environments, data center environments, or in SDN environment. So other features like segment routing is essentially very much used in service provider environment, and especially in SD-WAN environment. So in case of segment routing, what essentially does, it basically helps you in BGP driven traffic engineering. So it has many other features. One of the important features is BGP EP, egress peering engineering. So essentially what you do, you kind of put source-based routing using EP, where you actually calculate the path from your egress side depending on your traffic or bandwidth consumption, and then you signal your headend so that your headend can take a decision where to forward the traffic when your links are congested. Other stuff like slow peer management, AIGP, BGP flow spec, multi-S BGP, except on BGP origin validations are very important features and new features. So in summary, what we have seen is BGP is the glue which ties the AS-based internet infrastructure. So it's now not only getting used as a tool to transport your routing infrastructure, but essentially it has lot many use for next generation of services, especially in SDN, service provider and data center environment. So these are some references. I just thought of having it. Thank you. I thank you all for your time, and I hope it was informative.
All right. We have 5 minutes available for us to have questions. If anybody has any questions for the speaker, they're welcome to come up to a mic and do that. I know he was thorough, but maybe he wasn't that thorough for some of you.
Hi, I want to ask you about using the IBGP between the BECE.
Okay.
So what is the risk from doing that, and
You're talking
how
about
can
this-
you prevent loops in this case? Because
Right.
you are breaking the AS path.
Right. So what essentially it does
Filtering.
is within your P, right? What it does, your client side, it treats it as your internal client. So within the P, per VRF, it has to support RR kind of functionality. So same way as you look at RR, right? How it prevents looping. It basically adds different attributes so that loop doesn't happen. So in case of IBGP as your PEC protocol, essentially what you are doing, first you are providing within your per VRF on over the P RR kind of functionality, and then you are actually encapsulating all your IBGP or the customer attributes into something called attribute set. So your attribute set are something which are encapsulated, so it will not be visible over your service provider environment.
I think my question here is more, if you have any flabbing on the customer equipment side, now it will start to cause a flab in the whole domain because he's using the same ES path. So is that worth the risk? Because any instability now
No.
on the CE will cause the whole BGP to rerun
so-
again and converge.
Yeah, it cannot actually use the same AS path. It cannot
will-
use the same AS number. So if you see here, the
Oh.
AS number of customer is 200 and provider is 100.
So you run internal over different AS numbers?
Right.
And where do you see that supported? Is this supported in recent code or is this an old feature?
It is still RFC. It is still
Oh, it's
in
not
RFC.
supported yet?
No, it is
Oh,
still
okay.
in development phase.
Okay.
It's not
Thank you.
supported yet. Yeah.
Yep.
Rob Hagan, Zayo. Do you recommend any open source BMP servers, collectors?
Yeah, actually, one Open BMP, I guess, is supported or been distributed from Cisco. And what it does is supports the ODL controller, and it also supports your SQL kind of interfaces for the ODL controller. So essentially, what you can do, you can implement the Open BMP controller over the ODL controller, and then it will abstract the BMP information and provides you abstract data, so that you can use those for, let's say, automation or querying different attributes of which BMP. Those kind of functionality can be done. So yes, there is one Open BMP, which is very popular actually.
Any other questions? All right, I'm going to go ahead and close the session. Let's thank Rohit again for a great
Thanks
talk.
everyone. Have a nice
Thank
day.
you very much.